to today's lesson. Today we are on lesson 1-8. For today's learning objective, to find the sum of an infinite geometric sequence. Our language objective is to explain how we can find the sum of an infinite geometric sequence. So let's take a look at today's do now. Let's take a look at today's do now. Let's calculate the sum of the first 5 terms in the geometric sequence. So I want you guys to try this one on your own. Okay, so the sum of the first 5 terms of this geometric sequence is equal to 31. Let's look at today's thinking. How do we find the sum of an infinite geometric series? An infinite geometric series. Can we add up an infinite number of terms? Let's look at 2 geometric sequences to find the sum of all the terms. So the first one is similar to our do now. So I am going to find the rule for the nth term. So the rule for this sequence, to find the nth term, would be 2 raised to the n minus 1. I am going to graph this function. So I've put it into decimals, 2 raised to the n minus 1, x minus 1. And I see our function from left to right is increasing, right? It's exponential. So if you look at this function as the x's increase, as my sequence increases in value, so does the sum. The sum is going to keep increasing, which means that the sum as we increase, as we head to infinity, will also head to infinity. What this means is that the function diverges. That means that it never reaches a specific value. Alright, let's look at the second sequence. In this sequence, I'm going to start off the same way. I'm going to find the nth term rule. And here is the rule. We have 4 times 1/2 raised to the n minus 1. I am going to do the same thing I did before. I'm going to graph this. So let me look at this function. In this case, as my series decreases, at first my function starts decreasing, but then all of a sudden it stays and we have some asymptote. So it's reaching or getting very close to a specific value. So as we add up infinite amount of terms, where does this function go? It heads to a specific location. Let's get closer. It's looking like it's heading to 0, or getting very close to 0. Which means that it converges. All that means is that it makes it or gets very close to a specific value. So why does a function sometimes diverge and sometimes converge? It all has to do with this common ratio. In order to find the sum of an infinite geometric sequence, the sequence must converge. We use the following formula. So here's our formula. Again, the formula is given in your formula booklet, but the most important part here is when R is less than 1. More specifically, when the absolute value of R is less than 1. This will always occur. If the absolute value of the common ratio is less than 1, the function will converge. So let us try some problems. Example number 1. Identifying if a sequence converges. So determine whether the infinite geometric sequence converges. If so, find the sum. So first thing we want to determine is, does this sequence converge? So what we are going to do is identify our common ratio. So here, the common ratio is 1/2. If I use the absolute value of R is less than 1, we see that this comes out true, which tells us that this will converge. It will eventually reach a certain value. So since that is the case, I can actually find the sum of the infinite geometric sequence. So for this infinite geometric sequence, the sequence will reach a value of 40. Let's try number 2. For number 2, first thing we're going to identify is the common ratio. Alright, for number 2, the common ratio is 2. I plugged it into the absolute value of R is less than 1, and we see that it comes out false. Since it comes out false, that means this sequence will diverge. Let's look at example number 2. Example 2, finding the sum of an infinite geometric sequence. So it says, consider the infinite geometric sequence. Part A, find the common ratio. Part B, find the 10th term and an expression for the nth term. And part C, find the sum of the infinite sequence. So let's start off with the common ratio, which is easy. So I get the common ratio is equal to 1/5. I know that this will converge. For part B, we want to find the 10th term. Okay, so for part B, I used the nth term formula and I got a really small number, so I wrote it in scientific notation. For part B double I, we are trying to represent the nth term, an expression for the nth term. So I'm going to plug in what I know. So my nth term formula would be as given. For part C, we want to find the sum of the infinite sequence. So I know I can find the sum because I know this will converge. So the sum of the infinite sequence using our given formula, plugging in everything we know and simplifying. Okay, so for the sum of the infinite sequence, I get 125/4, or I can write the decimal value for that. So if I am doing this without a calculator, the fraction would be my final answer. If I have a calculator, then I could use the decimal value. So let's look at our last problem. Number 2, consider the infinite geometric series. 405 plus 270 plus 180. A. For this series, find the common ratio, giving your answer as a fraction in simplest form. Part B, find the 15th term of this series. And part C, find the exact value of the sum of the infinite series. So let's look at part A. So I get a common ratio of 2/3. For part B, we want to find the 15th term of this series. So using our nth term formula. Okay, so for part B, using my nth term formula, I found the 15th term to be 1.38732 and so forth. I wrote my answer using 3 significant figures. And last one, we want to find the exact value of the sum of the infinite series. We are going to use our formula. Plugging in everything we know. And it says find the exact value, so we are going to work with the fraction. And for the sum of the infinite series, we get a value of 1215. So that is it. Keep learning, keep growing, and I will see you in our next video.